All right. So till now we have discussed about the different Bayesian methods like Monte Carlo integration, accept reject, MH algorithm, right? Others. So now we will move to the bootstrap methods like that. So till now, when you just studying about the Bayesian or MLE or whatever the methods you have discussed till now, what was the basically idea behind that one of your Bayesian estimation or MLE? What was the idea behind that one? The idea was you have the samples like x1, x2, xn. That was your one sample. Okay, x1, x2, xn was your random samples. In each random sample, you had the observations. Like here, you had the observation x1 to x, uh, sorry, x11, x12 up to xn, 1n, and in x2 you have the random observations, the trials, that was x21, x22, and so on up to x2n, and so on up to x state m. xm is the sample. So here x m1, x m2 up to x mn. That was your random observation for each random sample, right? Do you understand the meaning of the random sample, how you estimate the parameter? I told you in the first lecture of the estimation theory when we just discussed how we reach from uh, classical to Bayesian. Do you remember that? In that one, I told you that expected value of theta cap is equals to theta, right? In that one, we said that it means that x bar is the unbiased estimator of theta, right? What is the meaning of that one? Means if I am going to take the sample x1, x2, xn, and I take the mean of that one, and that is equals to theta. What is the meaning of that one? What is the this meaning? Huh? X bar is the estimate of the theta. That was the concept for the classical. Even the Bayesian means I am say maybe you studied this theorem in your sampling theory, that sample mean. Did you study that one? Sample mean is an unbiased estimator. Unbiased estimator of population mean. Did you did you study this theorem? So what is the meaning of this one? I am going to take the sample x1, x2, xn, and I am going to take the mean of that one, the sample, and that will be equals to the population parameter. Suppose my population mean is theta, so x bar is equals to theta. Is it the correct interpretation of this theorem? Yeah. This is partially correct. This is not the exact meaning of this one. The meaning of this theorem, that sample mean is the unbiased estimator of the population mean, it means that you have the one sample, you collect the one sample, okay, x1. In x1, you have the observations, sample units, correct? That was your x11, x12 up to x1m. Right. After that, you will collect another sample. In that sample, you say it x2. In that one, what you will do? You will collect again the sample units like x21, x22, and so up to x2m. And so on up to n sample you will collect here xn. Here you will again collect the observations or sample units that are your x n1, x n2 and then x n m. This is your n samples. Okay, this is the meaning of xn sample. X1, x2, xn are not the observation. X1, x2, xn, these are your samples. Inside that sample, you will collect the sample observations that we call it the sample unit. All right. So you will calculate the sample mean for each sample. So that will be x1 bar, x2 bar up to x n bar. And after that, you will take the mean of all these means. That will be your x bar. That will be equals to your population mean theta. That is the basic meaning of your theorem that sample mean is the unbiased estimate of the population mean, right? But this theorem or this statement holds in the real life. Are you going to hold or are you going to apply this statement in your real life? Means if I'm going to make some curry or some vegetables I'm going to cook. So at that time, will I take the 1 spoon or I will take the again and again? I will take the 1 spoon of the to taste it again and again to check that whether the salt or whether the chili or other ingredients are in a proper manner or not. What I will do? I will take a 1 spoon or I will take again and again the sample. I will do again and again. Is this happen in the real life? We take only one. Mostly. No, we don't do that. We don't take again and again. If I will take it again and again, the entire curry will finish. What I will eat in the lunch or dinner, and what I will serve to others, if I everything will finish. Or if I just take the another example here from the medical science or from the producing the bulbs in the market. If I want to produce the bulbs in the market, okay, I am the owner of the bulb, any bulb company, electric bulb. So what I will do? I will put some bulbs on testing. I will measure that what is the failure time of each bulb. Then again I will put another lot for testing, and then again I will put from this theorem. I need to do this only, na? From this theorem, I need to follow this procedure that I will first I will take n bulbs and I will put them on the testing and I will check that whether they are going to fail on the time or not, on what time they are going to fail, and then I will find out their average failure time. And again I will put m bulbs on testing and I will note down their failure rate or failure time, and then I find out their average failure time, and I do it again and again. So it's a costly for me as well as I will face the losses, right? Is it practical in the real life? Is there any practicality of this theorem in the real life? I cannot do it, right? So at that time, the fundamental theorem of the statistics, like this theorem, sample mean is the unbiased estimator of the population mean, when you find out the MLE, so it fails in the real life scenario, right? Even though in the Bayesian, what we were doing, we were assuming that x1, x2, xn is the sample that follows some particular distribution, and with respect to that distribution, we have the parameters, and that those parameters also follow some other distribution, right? Some prior distribution, and based on that, we were finding the posterior density function, and then we were finding the estimates. So in that procedure, what we were doing earlier, we were also taking the x1, x2, xn sample in the Bayesian also. In Bayesian also, we were taking x1, x2, xn sample, right? So what we were doing, we were carry forwarding, okay, we were carry forwarding the same sample or same theorems that we were following in the classical to estimate the parameters. Yes or no? At that time, we were also taking the x1, x2, xn samples. right? If you remember in the questions, what we were writing? We were writing x1, x1, x2, xn was following the normal distribution with mean mu and variance given sigma equals to 1, and at the time we were saying mu was following some other prior distribution, right? So means at that time we were also talking about the x1, x2, xn samples. In that one we were calculating the we were basically calculating, or we were taking the sample units x11, x12, x21, x22, and xn1, xn2, and so on, like that. But if you just see this, we are failing in the real life situation, even though in the Bayesian. Yes, see, in the real life situation, I just as I give you the example right now, what we are doing, I cannot put 100 bulbs again and again on on testing to find out what is the average population failure time of my bulbs to produce in the market. First of all, if I will put 100 bulbs, one bulb will fail in 3 minutes, one bulb will fail in 2 days, one bulb will fail within a second. One bulb may not fail for next 5 years. It happens, you have seen in your houses, when you put some tube lights or some bulb in your houses, some bulbs just diffuse within a second as you put it on functioning. Some bulbs are not going to fail or not going to diffuse for next 4 to 5 years. You have seen in your life, no? Right or not? Yes or no? So at that time, will you wait as a company owner? Where should I wait for 5 years? Yes or no? I should not wait for 5 years. Second thing, first 5 years I am going to wait for those 10 bulbs, those 10 or 20 or 50 bulbs. I am going to put another sample of 20 or 30 bulbs. It will be, will it be time consuming and money cost is involved there or not? So I cannot take samples again and again. And I gave you the example of the curry. If I'm preparing or cooking some curry, so what I will do? I will just take a 1 spoon. If I will distribute it to everyone one spoon, so what I will serve? So this basic theorem is going to be failed in the real life. I cannot take that one again and again. So what I can do? I can take the 1 spoon. That is affordable. I can put 10 bulbs only for testing. My one sample, X1. Okay. I can put only 10 bulbs on testing. That much I can afford. But I cannot afford to put 110 bulbs 100 times. When we are saying X1, X2, Xn here, what we says, here we also says one thing, na, in the theorem of consistency, what we say, as n tends to infinity, means I am going to take 100 sample. In 100 sample, I am going to take 10 units. So how much bulbs I am going to put? 1,000 bulbs I am going to put on testing. Means the cost of 1,000 bulbs, the profit of 1,000 bulbs that I could get, the time investment. So on how many dimension I am getting losses, right? I am facing the losses in different points. Yes or no? So is it practical or not? Not at all. Right. So now you may, for at that time, what we do, we just use that one sample and we generate the sample from that sample again and again, from that only one sample only. And then we find out the estimates. So that is called as the bootstrapping. Now you understand why I didn't teach you the bootstrap before the Bayesian. Some of you asked the question, that in the previous years they were teaching the EM algorithm and bootstrapping first, and then they were teaching you the Bayesian. So in the Bayesian, again we were talking about the samples x1, x2, xn, but in the bootstrap, what is there? We have only one sample. Okay, in that sample, we have the number of sample units, right? So that is the basic idea of the bootstrap when we are lacking with the number of samples, right? So here, when do we need the bootstrap in the real life scenario? So here we just give you the some example that a small sample size. So in a medical researcher test a new treatment on only 12 patients due to the expensive trials like cancer, right? In the cancer, when you are going for the treatment, anybody is going to do the treatment, it's a very costly one, right? So all the people cannot afford the cancer treatment. So at that time, what will happen? You will not have the enough sample, enough large, right? At the time, you have only few sample points, right? And some diseases are there that are very rare, right? Yes or no? In the real life, we have some diseases that are very rare, means in millions of one, like that. So at that time, we don't have the enough data. So we have the less sample. So how I will just go for that one estimation. So classical method requires a large sample for center limit theorem to work. In the center limit theorem, what we say is, as n tends to infinity, fx will follows the normal distribution. But for that one, what we need the large sample. Here, what we have only 12 patients, right? How you will repeat those 12 patients? You have only one sample of 12 patients. You cannot take the different samples here. Correct? Yes or no? So second is the complex statistics. An economist wants the standard error of the median income. Do you have any formula for the standard error for the median? There is no formula exist for the standard error of the median. So how you will find out? Correct. So there you are lacking. Again, the third one is the non-normal data. Insurance claim data is heavily right right skewed with outliers. So if the data is heavily positively skewed, okay, heavy positively skewed or heavy tailed, you says, because if it is heavy tail, how will be the graph? How will graph look like for heavy tail? Do you have any idea? It will look like this. So what this observation you will call? These are the outliers. So if this is outliers are present in the observation, so at that time, can you apply the t-test or z-test? Because t-test and z-test depends on the assumption of normality. This what is the first assumption for the z-test and t-test? That x1, x2, xn, whatever the sample you are taking, that should follows the normal distribution. Yes or no? Right. So when you are going to find out the confidence interval or test you are going to apply, so it will be wrong definitely. You find out the asymptotic confidence interval, right? Do you know? We find out the asymptotic confidence interval when we are not able to find out the confidence interval for any particular data, any particular distribution, right? So in that one, in the formula, what comes? In the formula, it comes Z alpha by 2 when you calculate the asymptotic confidence interval, right? If your data is heavily positively skewed, how Z alpha by 2 you can include? You cannot include that one, right? So the solution is Bootstrap method. Bootstrap provides the valid inference in all these situations without complex math. All right. So now this is the another example that I took here. The Bayesian analytics. I shared the Bootstrap PPT with all of you. Have you seen that? Right. So estimate the ratio of the online to in-store sales. How you will find out the standard error of that one? Is there any formula for that one? And that is the only one sample. Whatever the online sales happened and whatever the offline sales happened. You are not going to repeat that one. If I have a company, I am running a company and I want to see that what is the ratio of my online sale and offline sale, right? So I have the one data only. If I started my company last year and I have the only 1 year data, so I cannot repeat it again and again. I have the only one sample observation, right? So, and second one is the quality control. Estimate the 90th percentile of the product lifetime from 25 sample. Okay, quantile estimation is tricky with small samples. So you cannot directly estimate the quantile estimation. MLE you can estimate mean and variance. How you will calculate the quantile? Do you have any formula for that one? Have you studied any formula for quantile estimation? I don't think so. Right. Third scenario is to get a confidence interval for prediction accuracy of a model. How certain are we that our 85 accuracy is reliable? How you will find out that one? Whatever the 85% accuracy you are finding, it is reliable. How you will find out? Right. Directly you cannot find out that one. And third one is the fourth one, the finance scenario of calculate the value at risk. Maybe you don't know about that one. This is we study value at risk in the actuarial science. Okay, when we just go for some claims and for some life insurance and other things or medical insurance, at that time we calculate the value at risk. Okay, so from 50 days of return. So financial data is heavy tail and normal assumptions fail here because actuarial science data, whatever the data you have in the actuarial science, it's always heavy tailed. Okay, so you cannot use the MLE or you cannot use the asymptotic theory here, right? And you don't have the samples. You cannot collect the samples again and again, right? For particular scenario, right? So bootstrap one method that work for all of these problems. So what is the fundamental problem in the statistics? We observe a sample x1, x2, xn from an unknown population distribution F. I gave you two examples right now, two or three examples. When I am, see, all these examples are from there. If, see, I am running a company. If I am putting 100 bulbs on testing, so what I will do? I have the electricity bill that I need to pay. Where we can do the samples again and again. So basically, what happened in the real life, it is very rare that we can do it again and again. But yes, we can do it, but it will be like in the medical. Okay, if I am having not I am having someone having the fever, patients have the fever. So what doctor do in that situation? First thing what the doctor do? He check the body temperature. So he will note down the body temperature, right? After few days, again patients will go after taking the medicine. So again he is going to check the temperature. So what he is having? He has the previous temperature. Now he has the temperature, and after 2 or 3 days after that again he has the body temperature. So in that one you have the object samples x1, x2, xn of different patients, right? Or like that, if I am doing a farming, okay, I'm doing a farming. Suppose I'm doing the farming of sugarcane or wheat or that one rice. So in that one, I want to check that how much rice I produce in one particular that one in what particular village or in particular area. So different farmers are there. I will take the sample from few of them, right? How much rice they produced in their farms, and next year again I will take that one. Okay, so this is the basically classical sampling or classical sampling theory. But in the real life, in some situation when we are in medical field or we are in a business field, so we cannot do all these experiments again and again. Every time it is not possible. Yes or no? Like I just gave the example of the bulbs. I cannot put the bulbs on testing again and again because I need to pay the electricity bill. My bulbs are only going to fail that I should sell in the market. That I am just putting them and without any earning any money. So that is the loss. So I cannot go for that one again and again. But for the rice, if I'm doing some research in the agriculture area and I want to see that if I am producing some kind of that one, what we say, some new technique in the market for farming. So at that time, what is there? There is no direct loss for me. I'm not going to face any direct loss. What I will do, I will just give it to the farmers that technique. Okay, you just use this technique for the farming and to produce some what we say rice or wheat or something. Okay, to produce all these things, and after that I will check it. So at that time I can take the sample from different people, or what I can do, if farmer have the 1 acre or 2 acre or 1 hectare or 2 hectare land, so I can split it into parts, right? And I will ask some farmers, okay, you will split that one into the parts like this. Okay, so suppose five farmers are there in the village. So one farmer has this land, one farmer has this land. Okay, three lands, four land, and five lands. Okay, so what I will say them? I will say them, okay, split it into the parts. Okay, split it into the parts, your land, and use my technique, whatever the technique I am providing you to produce the rice in the market. So here I have some units. I have some units from here. I have some sample units from here. I have sample units from there. So this is my one sample. This is my another sample from another field. Okay, field 1, field 2, field 3, field 4, and field 5. So what I am having? I am having the different sample units from each land, right? So now I have the repeated sample. Now I am having, suppose this is my x1. So I have the 6 observation or 8 observation from x1. Again, I have the 6 or 7 observation from x2. I have again 6 or 7 observations from x3. And I am having the 6 or 7 observation from x4. And again, I have the 6 or 7 observation from x5. Right? So now I have the sample x1, x2, xn, x2, x3, x4, x5. Right? But I cannot do it in the to produce the electricity bulb because I am the only owner. Okay, I am not saying that I am comparing two different companies. Maybe this question will come in your mind that why I'm not going to take two companies' data. Okay, I can take the means Philips are there, one company and another company, whatever the companies are there. So another company is there, and I can take the data from two companies. I'm not taking the data from two different companies. I'm talking about the one some particular company or one particular type of bulbs. So whatever the type of bulbs I am producing, definitely or maybe other company may not produce, right? So at that time, what will happen? I have the restriction. I cannot go for the collecting sample again and again at that time. Are you getting my point? What I'm saying, trying to say? Right. So in that procedure, so what is the basically thing is that in the fundamental problems in the statistics, we observe the sample x1, x2, xn, okay, from an unknown population distribution function f. Okay. So we assume that always when we just go for the statistical theory, we always say x1, x2, xn follows some distribution fx theta. We always say this, but in the actual life, do you really know the distribution of your observation in the advance? We never know. All right. So that's why we are saying that an unknown population distribution of f. All right. So what distribution my population is going to follow, I really don't know because I have the only samples. Right. I am putting 10 bulbs in the testing. Okay. So maybe my the failure time that they are going to take, it is basically suppose like this. So I can say it is gamma or it's variable, but this is for my sample that I collected. But I don't know about the population. Is either population is going to exactly have the same distribution or not? Right? I don't know about that one. So what is our goal in the statistics first? The estimate a parameter. So we need to find out the estimates of the parameter that is basically mean, median, like that, right? And quantify the uncertainty means what is the variance, means what is the variance, what is the standard error, like these things that we need to, we are curious to find out. Yes or no? Right? And construct the confidence interval of theta means, and another thing that we are interested in the estimation theory or in our statistical inference, that what should be the confidence interval means what can be the lower and upper limit of our theta, whatever the mean we are taking that we can tolerate, right? So what are the challenges that we face here? That is the sampling distribution of theta depends on the unknown population distribution f, the complexity of the statistic t that we discussed, that we cannot find out the standard error or estimate of the median or ratio, right? And population distribution is unknown in the real life situation, right? So often analytical solution doesn't exist, don't exist for them. First of all, we don't know what is the distribution of population. Second thing is that we cannot find out the estimate of the median directly, all right, or standard error of the median directly, right? We cannot find out the standard error of the ratio directly, right? And if the data is heavy tail, so we cannot find out the asymptotic confidence interval directly. We don't have any mathematical theorem for that one. All right. So why do we need the resampling method? So what are the restrictions that there? Asymptotic theory is there. In that one, what this is, it requires the large n to apply central limit theorem. We discussed this one earlier. An analytical formula only available for simple statistics means you have the mean, formula of the mean. Okay, that basically the sample mean is the unbiased estimate of the population mean. But do you have any formula, estimation formula for the ratio? The what is the estimator of the population ratio? Do you have that formula? We don't have that one, right? Distribution assumption often assume normality. This is that if n tends to infinity, x1, x2, xn will follow the normal distribution. That is the assumption that we are following. But we don't have the large sample. In the machine learning or deep learning, what we say? We have the big data. We have the data in GB, means millions of observations are there. But can I collect the millions of observations of the cancer patient's treatment? Machine learning or deep learning talks about the big data, where we have the data in the millions. But I cannot collect the big data or millions of the observation for everything, like cancer patients treatment or other aids or other things, other kind of disease are there, right? Or like producing the bulb in the market. I cannot go for the millions of the observations, right? So it fails there. So examples, statistics without the simple formula like median, correlation. Have you seen any theorem for that one? What is the estimate of the population correlation till this date? Right, ratio, trimmed mean. Have you seen anything, any theorem for those things? I have not seen till this date. Okay, so here I just took the example here. Suppose the scenario is there. This is related to the bulb or curry that I gave you. A polyester survey shows that 105,000, sorry, 1,500 voters on candidate preference. Okay, and 52% supports the candidate A. Now, question is that how reliable this estimate? I just took the survey of 1,500 voters that to which candidate they prefer. And in that one, 52% says that we supports candidate A. What is the ideal approach from this one? What is the ideal approach from this theorem? Theorem is that I conduct 100 independent polls. Each poll should have the 1,500 new voters. According to this scenario, I should conduct x1, x2, xn, and should be 1,000 independent poll I should conduct. In that each poll, I should take m equals to 1,500 voters and then observe variability across the poll. I should do this one. This is the ideal statistical inference theory. Yes. Do we really know? Do we really do this thing? What we do? We have only one poll. We just take 1,500 samples and we decide whether they are going to uh, uh, prefer candidate A or prefer candidate B or prefer candidate C and others like that. So what Bootstrap solution do here? Treat 1,500 responses as the mini population. Whatever the 1,500 I took, now I will treat it like a population. Okay, after that I will repeatedly take the samples of 1,500 respondents with replacement. I will generate the sample from this mini population again and again with replacement. Okay, are you getting this point? I think you are not.
So we this um only one of the expansion that should be more than once.
Yes, one water can occur more than once when I'm going to collect the sample again and again from this 1,500 waters. Okay, and observe variability in this simulated distribution. Okay, I will generate the variability in this simulated distribution. This will be my empirical distribution. Okay, then I will find out which candidate they are preferring more. Okay, that is the thing that I can do here. Again, I will take the another real life scenario. Recipe tasting that I just told you. So a chef tests a new recipe 10 times and it is going to give the quality score out of 10. So it is giving the score 7.2, 8.1, 6.9, 7.5 like this and so on. And average I got it, X bar is 7.65. Question, what the uncertainty in this question? I have only 10 observations, right? So this sample mean is not going to represent the population mean because this sample mean comes from the one sample. These are my sample units. All right. So what I will do, I will take the sample of 10 scores with replacement. And example, suppose I am going to generate the samples again and again. Okay, I will take the 10 observations from here. So what I will do, I took the 7.2. So 7.2 is going to occur two times. Here, if you just see, you are not finding 7.2 again. 7.2 is occurring only once. So what I am doing, I am taking the 7.2, 7.2 is occurring again. 8.1, 7.5, 7.5 is occurring again twice, while 7.5 was there only once. 7, 8.5, 7.3, 7.9, 7.9 is going to occur twice. And I will calculate the average. Now this one is 7.61. And I will repeat this procedure 10,000 times. Okay, I will take the average again and again. And whatever the standard deviation I will get of the bootstrap average, okay, I will collect x1 bar star, x2 bar star, and so on up to x 10,000 bar stars. So when I'm going to repeat the sample from this sample 10,000 times, okay, from this sample, now this is my mini population. I will generate the sample here, this sample, and I will generate this type of sample 10,000 times from these observations. Okay, so now I will have the 10,000 means. I will have the 10,000 means, correct? So now these are the 10,000 observation. I can find out the standard error with respect to 10,000 observation. Yes or no? Can I find the standard error with respect to these 10,000 means or not? I can find out. So whatever the standard error I will get here, that will be the standard error of the population. Yeah. No, what I'm saying that, see, when you have the sample, this sample you have right now, 7.2, 8.1, 6.9, 7.5, 8.3, 7, 7.8, 8.5, 7.3, 7.9. This is the sample that I have only. So this is the one sample with 10 observations. So I don't have x1, x2, xn. I have only x1. So what I'm going to do, now I'm going to assume it as a population. Okay. And I will generate the random sample from this population with replacement. All right. So one observation can repeat here, one observation can repeat more than once, right? So I will take this sample. Okay. Give me a second. If I just show you this one through the R, if I just show you, give me a second. Just try to understand with this thing. So I need to open this one. So we have This where we have this is my data set. Okay. This is my data set. Say I'm saying it as a capital X. So this is my population right now. Okay, this is my population. Correct. So what is the formula to generate the random samples? From the given data? Command is sample. Okay. So sample we are going to generate, say, from the X, okay, of size 10. Check here. Help. Sample. Data vector size. Replace equals to false. Probability is null. So what we need to do? We need to say replace is equals to true. Okay. We need to say here repeat is equals to true. Sample of size 10. Replace is equals to true. Correct. I am going to run this one. So this is my one sample. Okay. What I am going to do here, I am going to generate it in X, small x. R is case sensitive, so small x and capital X both are different here. So what I am going to do, I am going to do it again. So now the sample is different from the previous one. Earlier first observation was 7.2, 8.1, 7.3, now 7.0, 6.9, 7.0. Right? Now I am going to do it again. So now it is 7.8, 6.9, 6.9, 7.5, 7.5. I am going to do it again. So it is now 6.9, 7.8, 8.1, 6.9, 8.1. So what I am going to do, I am going to do this one 10,000 times. Okay, if I am going to do it, see, like I am going to do that mean of X 7.8, 7.73, 7.81, 7.68, 7.58, 7.73, 7.49, 7.71, 7.66, 7.73. So every single time I'm getting the different sample mean, right? So I will get these 10,000 sample means. Okay. I will get these 10,000 sample means. And after that, what I will do here, I will find out the standard error of those 10,000 sample averages. Standard error of these 10,000 sample means that I showed you in R, that whatever the sample error will be there of those sample, that will be the sample error approximate to the sample error of the population. Okay, whatever the sample error of X bar I will get here, that will be the sample error approximately equals to the sample error of the population mean, that is basically mu. Okay, when you have the only one sample. Okay, now you understand it, what we are trying to do in the bootstrap. Okay, so after that we will come to the how bootstrap was developed. So bootstrap was developed by the Bradley Efron in 1979. So it is not that much old method. This method was developed recently in 1979, right? So it was developed in the research paper Bootstrap Methods, another look at the jackknife. Okay. And this paper was published in the Annals of the Statistics in 1979. So if you want to read this paper, this research paper, or this method in the detail, you can find this research paper, Bootstrap methods, another look at the jackknife. Okay. And Annals of the Statistics, 1979. So what is the key innovation that they said here? They said that compute use the computer simulation to approximate the sampling distribution that are analytically intractable. All right. So what we are going to do here, uh, so basically before this work, all right, the we statisticians were relied heavily on the exact probability theory, means we should know the distribution of the sample properly. All right, second thing was the large sample approximation estimate asymptotic theory. We were reliable that n tends to infinity, then our sample will follow the normal distribution. Means we didn't have the idea if we have only one sample how we should proceed. That was the problem before this research paper was published. Okay, we had only derived the exact formulas like uh, sample means, sample variance. Okay, like that thing we can only observe at that time. Before that one, we could not, we couldn't able to find out the standard error of the ratio, standard error of other things, right? Or asymptotic confidence interval when we have the only one sample. So no formula was there before this paper, and use the asymptotic approximation. So we usually use the Taylor expansion and the limit theorems for that one. Like there was a one theorem that it was basically square root of n theta cap minus theta will follows will converge into the normal distribution with mean 0 and sigma square in the distribution. All right. For this one, we require the large sample. All right. And etc. So we didn't have anything. And another point was the limit to the nice statistic. It means that we had the only for mean linear statistics or MLE. These could we find out only at that time. We couldn't find out the other things at that time, right? And another one is heavy mathematical machinery. It was basically like that. Uh, we usually used at that time major theory and Edworth expansion and etc. These things when we had the heavy mathematical machinery. So we need the major theory at that time. Maybe you know about a bit of the major theory when we just talk about the sigma field, Borel sigma field, ring, and others, right? So at that time we need all these things. But after this paper, we didn't computer does the work. It means that at that time, instead of finding out the exact formula or exact distribution, we can simply go for the computation thing. Like we can generate the sample from one sample again and again, as I showed you right now. So that we could use, means we didn't know, we did not need the normality and non-variance and parametric form. All right, so Bootstrap was using that whatever the approximate CDF we are finding from the sample, that will be the population CDF. All right. So before that, what was the assumption we had? Normality should be there. Population variance should be known for the Z test. This is the condition, no? This is the condition. Population variance should be known. I didn't get that loudly. Not necessary here. Here, we don't need any assumption like that. Works for any statistics. Means If they give you the ratio, you can take the ratio again and again. If they are giving you the median from the sample, so you can generate the median again and again, and then you can find out the further things, right? So there is no need for that one. All right, median, quantiles, correlation, regression coefficient, survival, even though complex Bayesian summaries, you can use the Bootstrap, right? So after that, the third one is thing is that uh, democratize the inference. It means the before 1979, before this paper came, so advanced inference required the deep theoretical training. Like they need the basically the population distribution should be known. All right, parameters should be known. Right, mean, what is the mean, variance, parameters, all the things should be known at that time, and you should know the formula of all those things. Right. Like if you are having that one, what we say, sample mean is the unbiased estimator of the population mean. So at that time, you should know the formula of the sample mean. Right now, you don't need anything here. All right. So you can, anybody can use it right now. And who knew the statistics deeply, they knew the, what is the formula, what are the things there. They only could use the about that one classical estimation theory. But after this one, you what you need to do, you have the only one sample and you need to generate the sample again and again, and then you need to find out the median and all these things. So anybody can use it. All right, so that is the basic idea behind that one of the bootstrap. Okay, now comes to why we need the bootstrap. Okay, so named after the phrase that to pull oneself up by one's bootstrap. So, meaning is that achieving something seemingly impossible using only what you already have. So, whatever the sample you have, you just use it again and again, and you can describe the results for the entire population. All right. So, what is there? So, we have the population here. Okay, in this one, population F represents the CDF or distribution function of the population that usually unknown. Okay, uh, it could be any distribution, normal, exponential, gamma, and all these things. And in practice, whenever observe F directly, okay, we cannot use it. We cannot find out the CDF of the population directly from the population because we never have the complete population in the when we are going for the statistical inference, right? We never have the complete population. So if we don't have the population, how can we find out the exact distribution function of population, right? And so in that one, our goal is always to learn about the population parameters like mean and variance and standard errors, confidence interval, and sampling distribution. So after that, what we do, we just take the sample from the population and we have only one sample here. All right. So we compute, after taking the sample, we compute the sample mean, sample variance, MLE, whatever we want to compute. And now the problem that will arise after that, we have only one sample, so we cannot directly see the sampling distribution of the theta cap. So if we have the theta cap is our parameter, theta is the parameter and we are estimating theta cap. So if we have only one sample, so we cannot have the exact sampling distribution of the theta. To find out the sampling distribution, again, we need the different samples, sample x1, x2, xn, right? But here we don't have different samples. We have only one sample. All right. So in that one, what we do after that, we just take the resample from the boot. So since we cannot resample from the population F, okay, because from the population we have only one sample, so we cannot take the different sample from the population, right? So what we will do, we we approximate it by using the empirical distribution. So we will take the sample again from the resampling from the sample. All right. So now what we do, we will draw the bootstrap sample, that is the sample with replacement from the sample again, and each bootstrap sample has the size n, and we assume that means we will take the sample x1, x2, x1 star, x2 star, and so on of the size n. Okay, each of them have the sample size of n, right? And we assume that here that x1 star, x2 star up to xn star, it will follows the empirical CDF. It will follows the empirical CDF f star, f cap. This is the empirical CDF. All right. So for each bootstrap, we compute the theta cap. All right. So means as I showed you in the R code, what we did at that time, we were taking the sample from the our sample again and again. And what we were doing at that time, we were finding the sample mean. So what we will do, we will calculate the theta cap star, that is our estimate from the sample that we are going to generate from the resampling, means bootstrap, that is your t x1 star, x2 star up to xn star. Here x1 star, x2 star, xn star, your bootstrap sample that you are generating through the resampling from the sample. Okay, right. Do you want a break? Okay, we will take a break of 5 minutes, then we will start. All right, so we were saying that we were discussing that we take the sample with replacement, and each bootstrap sample has the size n, and we assume that x1 star, x2 star up to xn star, that are the bootstrap sample from our sample resampling, follows the empirical CDF f, and for each sample we are going to compute the theta star. All right, means our sample statistic. We have the parameter and the statistic. So we are going to compute the statistics. It may be median, mode, or sample mean, or sample variance, whatever we want to compute, we will compute with the respect to each sample. All right, and we will repeat it around 1000 times. All right, there is no standard number of iteration is written in the theory, and they didn't provide any uh, standard number, okay, that we should repeat that number of times. But they said in the F1 paper, they said that we should repeat it at least 1000 times. In the 1000 time, it will converge. Okay. But we cannot say that exactly 1000 is enough or more than enough. Okay. Maybe we need sometimes more than 1000 iteration, or sometimes maybe we need only 1000. All right. So, but they said minimum 1000 repetition is we need to approximate the population CDF. All right. So we will repeat it 1000 times, and it will give us theta 1 star, theta 2 star, and up to theta 1000 star. All right. And this approximate the sampling distribution of theta cap. All right. It will provide us the sampling distribution of theta cap. All right. And after that, there is a one important thing that learn about F. All right. What is it basically? Mathematically, it is like we use the bootstrap distribution to learn about the properties of the population CDF. All right. We use the empirical CDF that we generated from the theta 1 star, theta 2 star to theta Haugen star, and we just know about the properties of the population CDF, and mathematically we represent it like the likelihood of theta cap is approximate to the likelihood star of the theta cap star. All right. So theta L star theta cap star will approximate to the population likelihood. All right. So here the empirical CDF that we are saying, it places the probability, this empirical CDF that we are going to generate from this one, it is going to take the probability 1 upon n on each observed data point, because we are going to take the sample with replacement. So what is the probability of occurring one observation? If we are taking the n sample, so what is the probability of occurring one observation if we are taking with the replacement? That will be 1 upon n, right? Because every single time there is a chances to occur the same sample observation. So that's why it is 1 upon n. All right. Now comes to the next point, the mathematical foundation of the bootstrap, that population versus sample. So we have the population CDF, that fx equals to probability of x less than equals to x. That is the standard formula of the CDF, but this is unknown. This is unknown for us. So, and we have the unknown parameter theta, that is the function of CDF. That is not the single observation value, but this is the function of CDF. And after that, what we do, we take the sample and we estimate the sample population mean based on the sample mean. Like we have the population theta, if the theta is the population mean, so we approximate it by the expected value of x. And similarly, population median, that is theta equals to f inverse 0.5. What is the median? Where the probability is half, right? So that's why 0.5. So sample is x1, x2, xn follows the are the IID random sample follows the distribution from CDF-F, and estimator is theta n is basically function of x1, x2, xn. In the sampling distribution, what we have, the sampling distribution of theta n depends on the f, and suppose sampling distribution of theta n is gf, that is induced by f. Our goal is to approximate gf without knowing the f. What it means basically, when we are saying that gf is a distribution induced by f, it means that theta cap n depends on random data. Okay, depends on the random data, and theta cap n will be a random variable. All right. So here, when we say that GF uh, is induced by F, it means that why? Because if F is normal, we don't know what is F exactly, because we don't know about the population. But if F is normal, so definitely our sampling distribution. All right. So the sampling distribution will also, the sampling distribution may be normal. All right. If capital F, the CDF, population CDF, is skewed, so sampling distribution may be skewed, right? Because we are going to approximate the population CDF through the sampling distribution, right? Similarly, if population CDF is heavy tail. So sampling distribution may be heavy tailed. All right. So that's why we are saying that the sampling CDF G is basically is a distribution induced by the population CDF F. Right? Because the sample, that one sample we calculate, we are taking here, right? The one sample that we are taking here, that is coming from the population. If population is normal, so definitely whatever the CDF we will generate from the bootstrap resampling, it will be normal. It should be normal. And whatever the, if the CDF is positively, distribution is positively skewed, so population sample distribution should be positively skewed. If the sample population distribution is heavy tail, so sample distribution should be heavy tailed, right? Because when we are talking about the sample, what is the sample? Sample is not only one part. Sample is only one part of the population, but that is the truly representation of the population, right? What is the sample? Sample is the truly representation of the population. If we have the some outliers in the population, so we should have some outliers in the sample also. If our population is normally distributed, so our sample also should follow the normal distribution, right? If our population is positively skewed, so our sample should be positively skewed. For example, if your class is there, or any class is there, in that one students are there, so what is the assumption about the marks of the students? It is normally distributed, means few students are there who are very poor in the study, and few students are brilliant, and mostly are living in the lying in the middle. So here what we are going to do, when I'm going to take the sample, so in that sample I should take few are good or few who are poor and few more who are lying in the middle. So again, when I'm going to uh, draw the graph of the marks of my sample, that should also look like the normal, right? So when I'm going to take the sample from this sample again and again, so it should be look like a normal distribution, right? So the same thing I'm going to do here. So that's why I'm saying that GF is induced by the F. All right. So now we will come to the next one, the empirical CDF. Okay. So the empirical CDF function, what is the empirical CDF function? So if I am having the given the sample x1, x2, xn is my sample, the empirical CDF function is fn x cap is defined as 1 upon n summation I goes to 1 to n 1. 1 is the indicator function here. Xi should be less than equals to x. That is hash I such that xi should be less than equals to x divided by n. So means I will take the values, or basically it is like the count how many observation, what it is counting here, count how many observations fall below x. Okay, divide by the total number of sample size n. All right. So here I will take the indicator function. Indicator function 1, xi is less than equals to x is defined as it should take the value 1. If xi is less than equals to x, it should take 0 otherwise. Right. So at that time, what will happen? I will have the observations here. When I will take 1, so x1 will come, If x1 is less than equals to x, then x2 will come, that is less than equals to x. So what I will get? I will get the observed observation like this: x1 that is less than equals to x2 less than equals to up to less than equals to xn. So that will be my observed sample in the empirical CDF because of the indicator function that I am taking. Right? If it is not small, then it will removed. Otherwise, if it is small, then I will keep it. Right? So here, what I am basically doing, what is the property is that f cap nx is a step function with jump of size 1 upon n at each xi, means it is a discontinuous function. Because all the observations of x we are not going to take. We are going to take only those observations from my sample that are less than equals to x. If they are not less than equals to x, I will remove them. Right, so that's why it's a discontinuous function. It is a step function with the jumps of size 1 upon n. Right, here fnx puts the probability mass function, all right, of 1 upon n on each observation. It means the ADF, empirical CDF, can be written as f n cap x equals to summation over the range of I goes to 1 to n 1 upon n delta xi of x, where this delta is the point mass at xi. This is a point mass at xi, capital Xi. All right, that is basically, it means probability of x, capital X equals to capital Xi is 1 upon n. The probability mass of xi here is 1 upon n because the probability of selecting each observation here is 1 upon n because we are taking the sample with replacement. Right? Here, what is the empirical CDF is here? Empirical CDF measure the proportion of the sample observation that are less than or equals to x. So in that one, Fn star, Fn cap is the non-parametric MLE of F. So how we will define this one, this point? This is basically Fn cap x follows the properties of unbiasedness. Follows the property of unbiasedness here. So what is it basically? The expectation of f n cap x is equals to fx, not fnx, fx, the population CDF. All right. And the variance of fn x cap will be equals to fx into 1 minus fx divided by n. That will be the CDF of your empirical. This will be the variance of your empirical CDF, right? And in that one, n, f, and x will follow the binomial distribution with parameter n is the size of sample and probability of success will be your CDF fx. Right. So that will be the distribution. While you are going to take, because 1 upon n is the probability. What is the probability of this one? Selecting observation here is 1 upon n. Right. So that's why n into f and x will follows the binomial distribution. That is the property of your empirical CDF. So here you can see the empirical CDF that we are drawing here. Okay, this is the visualization of your empirical CDF with corresponding to the true CDF. Have you ever tried the case plot for the model fitting? Have you ever seen case plot? All right, so what we do, we have the true CDF of the population and we try to check our approximate empirical CDF method, and we find that whether they are nearby to each other or not. If they are nearby to each other, we say that the model is fitting well to the data, right? So here what we are doing, we are assuming that we draw the exponential type CDF, that is our population CDF fx is equals to 4 1 minus e raised to the power minus 0.3 x. This is our CDF. Okay, that I am assuming for 5 observations. N equals to 5 I am taking. Okay, so what we are doing basically here, we took the sample and we are going to start them to shorted them in the order statistics in that one, like x1 is less than equals to x2, less than equals to x3, and less than equals to x4, and less than equals to x5. Do you understand what is the meaning of this one? Why we are writing x1 in the bracket, 1 in the bracket, and x2, 2 in the bracket? What is the meaning of this one? Huh? Order statistics. Do you understand the meaning of this one? So it means that x1 is my observation that should always less than x2. When we are saying x1, x2 is my observations and up to xn is my observation, we never claim that x1 is less than x2. X2 may be less than x1. Okay, or xn may be the lowest value. All right, when I'm putting 10 bulbs on testing, so at that time I will collect their failure rate. So 10th bulb can be failed before remaining 9, right? So at that time x10 will be my smallest value, observed value. So that's why I represent that in the 1 in the bracket, x1, x2, xn, like that, lowest value. So x1 can be my xn variable. Okay, whatever the x1 I am writing here, x1, that comes from, maybe comes from the nth bulb. Okay, x1 doesn't mean that this is first bulb. It can be nth bulb, any bulb. Okay, but this is the lowest observed value. That is the meaning of that one. So I will observe that one. And why we are going to shorted them in the order here? Because first thing is that the empirical CDF. Okay, empirical CDF jumps only at the at the observed sample points. Okay, so means empirical CDF will take only the next value when you are going to observe the x. Means your CDF fnx cap x, what we defined is, we defined it as the xi, capital Xi should be less than equals to x divided by n. When my xi, my sample that I'm going to generate, it is less than equals to x, then only it will move further, my CDF. If it is not less than, it will not move. It will remain here only, right? My empirical CDF will not move further till I'm not going to get the value of xi that is less than x. Yes or no? So that's why empirical distribution function jumps only at the observed sample points. Okay. Second thing is that here order statistics determine the determine the steps location. Determine the step location. Okay. So here you can see that in empirical CDF, that first is this is non-decreasing, it is increasing continuously, right? Second point is that it is right continuous. Third thing is that it is point-wise constant, right? It is point-wise constant. It is not going to change, right? So it is a step function because when x increases, okay, when n is going to increase, no new data point. If we don't have the no new data point, so at that time empirical CDF will remain constant, that I said you earlier, right? And it will pass a data point. So when it will pass the data points, it is going to pass these data points. So next empirical CDF you will get at that point. So it will jump. All right. And each jump with the probability 1 upon n it will have. So here I am going to take n equals to 5. So what will be my points? First will be 0.2, second will be 0.4 because it will 1 upon 5, second will be 0.6, another point will be 0.8 and then 1. All right. So you will point out these points 1 upon 5, 2 upon 5, 3 upon 5, 4 upon 5 and 5 upon 5, that is your 1. So that is your empirical CDF. Okay. This is your empirical CDF. So if you just see here, what is the key point? As n tends to infinity, empirical CDF f n cap converges to the true f. So here you will find that they are approximate. As n is going to increase, the distance between both of them is going to decrease, right? So it basically means that the empirical CDF converges uniformly to the true population CDF. So that is the basically idea behind the empirical CDF. How you are going to find out the empirical CDF from your sample, and you will estimate it for the population, right? So now here we have some theoretical properties of the empirical distribution function. So for that one, we have first one is the Gilvanco-Cantelli theorem that was given in 1933. So what they say is that the thing that I said earlier, the empirical CDF converges uniformly to the true CDF almost slowly, means if you are going to take the supremum of x as n tends to infinity, you are going to take the difference of empirical CDF with respect to the empirical CDF and the your population CDF. So it will be asymptotically tends to 0 as x is going to increase. Okay, for n tends to infinity. Means if you are going to take n tends to infinity, means you are going to take the sample, large sample. You have one sample, but you are going to take the large one again and again, and you are going to take, and for the supremum value of x, what is the supremum value of x here? Supremum value of x is here, this one. Here you have the supremum value of x, correct? At this point. So when you are going to increase that one at the, and you are going to increase x so on, and you are going to take it further, so at that time it will be difference will be 0 when you are going to take n tends to infinity. This is your x5. When you are going to increase it, x5 up to x 1000. So at that time, the difference between both of them will be 0. So at that time, your empirical CDF will converge to your population CDF, right? That is the meaning of this theorem. All right.